Hello and welcome to Unit 12 on rotational kinetic energy, torque, and equilibrium. As I did in Unit 11, I want to begin by comparing where we are linear versus angular variables. In Unit 11, we looked at position, velocity, acceleration, and mass. This unit, Unit 12, we're going to look at the angular equivalents of force, kinetic energy, and work. Those become torque, rotational kinetic energy, and work as well. In this first part of Unit 12, we're going to begin by looking at torque. So what is a torque? A torque is something that causes a rotational motion, just like forces cause a translational motion. So here I have drawn a bar with an axis of rotation. I can apply a force to this bar to get it to rotate, but I have to do it correctly. If, for example, I apply a force by pushing in here, the bar will not rotate. Consider if this was a door, you're pushing on the end of the door inward towards the hinges. It doesn't rotate. If I want to get the door to rotate, typically you would put a force here. And if you want that force to do as much as possible, you want that force to be perpendicular to the line that comes from the axis of rotation to where you're applying that force. You could also apply a force down here. This will also cause the object to rotate, but it's not going to rotate as well as if out here. So this motivates the idea that there is more to torque than just applying a force. Not only does it matter where you apply the force, but at what angle. Okay. So torque, by definition, is a vector, and that vector is given by R cross F, where you apply the force and how big the force is. And the cross product takes care of the directionality. You may remember that for cross products, you can find the magnitude by taking RF sine theta. In this case, the angle theta is going to be the angle between the radial vector and the force vector. So the radial vector points from the axis of rotation to where the force is being applied. So for this little f here, my r is there. So we can see here I have an r. I'm going to move my r down. Here is my 90-degree angle. Sine of 90 is 1. Alternatively, I'm going to erase a little bit here so that we can draw a prettier picture. If I were to, at the end, apply a force, here's the r vector, that is going up like this, then there is the angle theta, the angle between r and f. So a question: can a small force exert a larger torque than a larger force? And the answer is yes. Okay. So remember, torque equals RF sine theta in magnitude. Oh, I don't need vector signs because it's a magnitude. If F is small and R sine theta works out to be or if a small force multiplied by r sine theta could possibly result in a larger torque than a large force multiplied by a different value at a different sine theta. So for example, if we go back to the previous example we were thinking of, if I have a small force applied here at 90 degrees versus a large force applied here, this force causes no torque because you have a sine of 180 degrees, which is 0. This force causes a torque of RF times the sine of 90, which is just RF. So yes, a small force can cause a larger torque than a large force, depending on how it is applied relative to the larger force. Let's consider now an example. Here I have a rod that is going to rotate. I've got two forces applied to it. F1 at the end at an angle of 115 degrees and F2 in the middle at, or roughly the middle, I guess, at an angle of 30 degrees. I can find the net torque much as I find a net force. I just add up all of the forces applied to an object. So this would be torque 1 plus torque 2. Torque 1 is going to be the torque from F1. So that will be 6 meters times 3 newtons times a sine of 115 degrees in magnitude. Remember, torque is RF sine theta. And that works out to be 16.3 Newton meters. Torque 2 will be at 2 meters times 10 newtons times the sine of 30 degrees, and that works out to be 10 Newton meters. I know the magnitudes of the torques at this point, but I need to find the direction. To find the direction, I need to use the right-hand rule. So remember, for the right-hand rule, you stick or you point your fingers of your right hand in the direction of the first vector. In that case, that is R. In both cases for here, R points to the right. For F1, I want to do it with my palm sticking up. That gives that torque 1 is going to be out of the page at you. For F2, I want my palm pointing downward so that I can point into F2. That gives me that torque 2 will be inward. Therefore, when I find the net torque, I want to subtract. And I'm going to choose to let an outward torque be positive. So this will be 16.3 Newton meters minus 10 Newton meters, or 6.3 Newton meters directed outward. Just as we had for our forces, we can write a version of Newton's second law in angular form. So remember, Newton's second law told us that the net force acting on an object was its mass multiplied by its acceleration. To get the angular form, we let the net torque equal the moment of inertia multiplied by the angular acceleration. So F net equals ma becomes the net torque equals I alpha. Let's do an example where we work with this. Here we have a rod. In one case, it is rotated about the center of mass. In the other case, it's rotated about an end. Looking at the table of moment of inertias that was provided with Unit 11, we see that the moment of inertia about the center of mass is 1/12 times the mass of the rod times the length of the rod squared, whereas the moment of inertia about one end equaled 1/3 ml squared. We are also told that in this case, whatever the torque is applied gives an angular of acceleration of 8.1 radians per second squared. So the net torque about the center of mass will equal the moment of inertia about the center of mass multiplied by the angular acceleration for this case. We are told in the problem that the torque was applied, or the same torque was applied in both cases. So I'm going to call the torque about the center of mass just equal to the torque. The moment of inertia of the center of mass was 1/12 ml squared. And the angular acceleration in this case was 8.1 radians per second squared. This simplifies down that the torque applied is 0.675 radians per second squared times the mass of the rod times the length squared. I also know that the torque about an axis has to be the moment of inertia about the axis multiplied by the angular acceleration in that case. Should really subscript those two. But again, in the problem, we're told that the same torque is applied in both cases. As we saw, the moment of inertia for a rod about one end was 1/3 ml squared. And that has to equal the new angular acceleration. Plugging in that the torque is the torque in both cases, the mass times the length squared is on both sides of the equation, so it cancels. And that allows me to calculate that the angular acceleration about an axis on the end, in this case, will be 2.025 radians per second squared.